Hi, my name is Usha Patel. I lead the LED lighting initiative globally within Littelfuse, and I'm excited to talk to you today about this emerging and fast-growing technology. We'll cover protection standards for both indoor and outdoor lighting. We'll talk about protection technologies and what types of parts will pass these standards. We'll also look at some schematics and block diagrams of indoor and outdoor lamps and lighting fixtures. Finally, we'll look at all the support tools Littelfuse has created for engineers who are designing these kind of protection circuits. Let's first start with the LED retrofit lamp and the indoor consumer lighting market. As many of you may have heard already, the incandescent lamp is being phased out in many countries, starting out with the 100-watt lamp, going down to 60, then 40-watt lamps. In Europe, for example, they're phasing out the 40-watt lamps today. This measure is estimated to save millions of kilowatt hours a year in the US alone. We've created a summary matrix that shows protection standards in many key geographies in the world. The protection has two parts. These standards have a surge immunity piece and a safety piece. By safety, we mean overcurrent. It's short circuit overload protection. By surge, we mean overvoltage, to protect against events as those created by lightning. So let's take a look at the US column, for example. The surge specification contained within Energy Star addresses all the LED retrofit lamps and certain indoor lights. In the US, the safety specification is UL 8750. And for outdoor lighting in the US, there's a DOE surge specification. It's a 20 kV, 10 kA specification that most outdoor lighting systems need to comply with. It is forecasted to become an ANSI NEMA specification shortly. Let's talk about safety a little bit. UL 8750 is a recently created standard for safety of LED equipment for use in lighting products. The purpose of UL 8750 is to minimize the risk of shock and fire. It actually calls for an overcurrent protector device to limit the current or interrupt it in a short circuit or overload condition, and actually specifically calls out fuses as a technology. Fuses are the most widely used and most reliable technology to protect against short circuit and overload. Let's look at surge for a second. Energy Star is a specification. It references IEEE C.62.41 in the US, and it's mainly used to surge test LED retrofit lamps. The purpose of Energy Star is to emulate a field transient condition, such as an indirect lightning energy, in the form of a ring wave. So it uses 100 kilohertz, half a microsecond ring wave at 2.5 kV, 83 amps, which is class A. The lamp is connected, it's lit, it's hit 7 times in common mode and 7 times in differential mode, 1 minute apart, and to pass the test, the lamp must stay on through all these surge strikes. It's a relatively easy test to pass. It's not very high energy. Littelfuse has many fuse and MOV options as a coordinated solution that'll help pass in different form factors and sizes. We've helped many customers in North America get Energy Star for their bulbs. Outside of the US, the most prevalent surge standard is IEEC C.62.41-2002. It's different from Energy Star in that instead of using a ring wave, it uses a combination wave, an 8 by 20 microsecond short circuit current and 1.2 by 50 microsecond open circuit voltage. And this waveform emulates surge conditions caused by lightning, for example. So for lamps below 25 watts, it's a 500 volt 250 amp test. And for those above 25 watts, it's a 1 kV 500 amp test. There's more energy under these waveforms than we saw in Energy Star. Again, Littelfuse has many fuse and MOV options that'll easily pass IEEC 61004-5. Now that we've discussed both surge and safety requirements, how do we protect against them in an actual circuit? So here's a block diagram of a typical retrofit bulb or an indoor lighting circuit. You have your AC coming in on your left. It's generally coming in at 120 volts or up to 240. And that's where you put your safety device. You have your AC fuse in there coordinated with an MOV. So your fuse is going to provide your short circuit and overload protection. Your varistor, your MOV, is actually going to provide your surge suppression. So the fuse and the MOV need to be a well coordinated solution, in that when the MOV is actually clamping the surge energy, the fuse shouldn't open. It should be able to withstand the energy under that waveform. Let's move on to the right. You'll see a TVS diode right after the bridge rectifier before the input into the DC-DC converter. Certain circuits might need a TVS diode in their application depending on the sensitivity of their ICs downstream. For example, your LED driver might have a low voltage tolerance, and you need the TVS to further clamp down the voltage before going into the converter. On the right, certain circuits have used PTCs. In essence, it's a variable resistor. And PTCs provide over temperature protection for the LEDs. They actually help in stabilizing constant current designs where they sense the temperature of the LEDs and they vary their resistance to limit the current. Here's a complete part selection guide organized by surge level needed to pass. So simply you would look on your left-hand column, you'd identify which surge level you need to pass. You would look across to get your fuse, MOV, and TVS options. These have been tested extensively, and the fuse and MOV options actually are a coordinated solution like I mentioned before. You can't just pick any fuse and combine it with a varistor. We need to make sure that they act correctly in the circuit where one doesn't open prematurely. Let's talk a little bit about commercial and outdoor lighting. These kind of lighting systems are far more susceptible to environmental events such as lightning. So the protection standards are far more stringent, in turn requiring a lot more protection in an outdoor luminaire, for example. The Department of Energy has created a model specification that's vastly being adopted by cities and municipalities in their RFQ bid packages for their street lighting retrofits. These call out surge immunity specifications that are very stringent. And this model specification may become an ANSI NEMA spec in the near future. This information is available on the energy.gov website under solid state lighting. This DOE spec calls out or references an IEEE C.62.41 surge specification. It references portions of that specification, as well as UL 8750 for safety. Let's discuss the surge specification a little bit more. First, the location of the LED light is actually going to determine the category level that applies in this IEEE spec. So category A is indoor, commercial building, office, retail. Category B and C low are the same levels. They're 6 kV, 3 kiloamp, and they are lighting near service entrances or commercial office building, parking garage type lighting. And C high, outdoors, is the key specification that the Department of Energy calls out for their LED Roadway spec. It's a 20 kV, 10 Ka combination wave. Difficult test to pass. We'll talk about that more on the next slide. Here's more detail on the surge specification. First, it's a combination wave. The surge is generated by a 1.2 by 50 open circuit voltage, 8 by 20 short circuit current combination wave. It's at 10 kV, 10 Ka. In reality, it's actually 20 kV, 10 Ka because you need a 2 ohm source impedance to generate the waveform. It calls for a total of 30 strikes. This is a key change from past years where it could be 1 or 2 hits. Now it's 30. It's very difficult to pass. It's in different coupling modes, and each line configuration, which will contain a varistor that'll actually help pass the surge requirement, line to ground, line to neutral, and neutral to ground, is going to take 10 hits each out of the 30. It's a high energy surge upwards of 1600 ampere squared seconds. The Department of Energy, besides the Municipal Street Lighting Consortium, also presides over the Commercial Building Energy Alliance. These guys are in charge of doing the parking lot and parking structure surge specifications for outdoor lighting. So there's 2 different levels, C low and C high, that they address. It's a 6 kV 3 kiloamp for C low and 10 kV 10 kiloamp again for C high. Same surge spec that we just discussed. Now that we've talked to you about the standards, how do you protect your lighting system and meet these standards? So here's a block diagram of a typical outdoor luminaire. On the left-hand side, you have your AC coming in at the input. You have your line, neutral, ground conductors. You have generally 120, 240, or 277 volts AC coming in. There's a high surge withstand fuse that's in development today that can be used in front of your surge protection devices, your cluster or your module. And the surge block actually contains 3 varistors. We talked about the different line configurations. Each varistor is going to take 10 hits, the line to neutral, neutral to ground, and line to ground. These varistors need to be minimally sized at 25 millimeters to be able to sustain the 10 kiloamps of current called in the DOE specification. Let's move on to the right. Right after the line rectifier, again, you have your TVS diode. Serves the same purpose as the retrofit design. It's for further clamping and to protect the downstream sensitive electronics that might have lower voltage tolerances. On the very right, you have your PLED protector device. It's a neat part. It actually serves as a bypass for open LED string, and it's widely used in high reliability applications. In an LED string, several of the LEDs are in series, meaning if one LED fails in the string, the whole string turns off. Using a PLED protector, you bypass the failed LED and the remaining LEDs stay lit. So it's really for high reliability. Again, Littelfuse has compiled an extensive list of parts that have been tried and tested to all of these surge conditions. They've been tested to even slightly more stringent levels than the DOE specification. So on the left-hand side, you pick the surge level, you move across to pick your fuse, MOV, TVS, and PLED options that come in many sizes and form factors. Littelfuse today has the widest selection of protection devices in the industry. Finally, we have a series of support tools. We have a comprehensive LED protection design guide. It's an interactive ebook. It contains selection guides and all the industry standards we talk about in more detail. It contains schematics. It compares different circuit protection technologies, the pros and cons, all the design considerations for engineers that are designing in these components, and test data from different applications and protection technologies as well. We also have online LED lighting resources. We have the Speed to Design website and can be accessed through the Littelfuse site, and several published articles on LED lighting in key publications such as EDN and EE Times, and a lot of the distributor publications as well. We have one of the most coveted tools, the LED lighting protection sample kits. We have a low power kit for consumer lighting applications, retrofit lamps included, and then we have a larger, more robust commercial and street lighting protection kit as well for use of our design engineers in their labs. We also do application testing in our Littelfuse labs, and we have the ability to test up to 10 kA surge levels. And finally, we have the best-in-class application engineering team that are available to provide expertise on all the protection options, design considerations, all the coordination requirements in the circuit. Really, these guys have a vast amount of expertise in the protection area. So I hope you found our protection discussion worthwhile. It's really a fast-growing, emerging market. It's exciting to talk about it. We're really looking forward to supporting your upcoming protection needs. Please give us a call. Thank you very much for listening.